Welcome, y'all, today to my talk. We're going to be talking about crash reports. As Patrick mentioned, my name is also Patrick. Great name. Might know me well from the Objective-C Foundation, also the creator of the Objective by the C conference, the author of the Mac malware analysis books, and most recently engaged in a new venture, W. We're building integratable components for Mac security products. But this talk is not about me, even though I'm up on stage. It's really all about you. So we're going to start with some very brief audience engagement. Just raise of hands. Who here already deeply loves crash reports? Yeah. OK, wow. All right, that's good. Like a crowd that's kind of on my side. And for the rest of you, I like a challenge. We'll see if we can sway your point of view. So what we will talk about today is just how amazing crash reports are and how we should all be ingesting them, reading them, loving, hugging them, and all the good things. So while we will be focused mostly on understanding crash reports and the value that they provide us, we will also be talking about some reverse engineering topics, et cetera, et cetera. But really, my main goal is to have us all leave with a deep appreciation, a love of crash reports. Now, you might be wondering, why should I care about crash reports at all? And this is a valid question. I'm going to go through and point out some different groups, different scenarios where we will see crash reports are very valuable, which includes users who report bugs that they can find in crash reports, developers who ingest crash reports to fix bugs, sysadmins or security teams who should be analyzing crash reports to potentially uncover failed exploitation attempts or even malware, and I'll also show you how hackers are very fond of crash reports as well. So let's start with users and developers. This is probably the case where most of you are already familiar with. So in a nutshell, a crash report is generated when there is a vulnerability or some issue in an application or program. The operating system will build a crash report. From users' point of view, this is mildly annoying to downright frustrating, right? Imagine you're working on a document in Microsoft Word. It crashes. You lose all your work. That sucks. Well, a crash report will be generated, and in that crash report, as we will see, we'll have all the details, the technical information that the developer is going to need to fix the bug. Why they crashed in the first place. So it behooves users to at least know about crash reports and perhaps submit them to the developer, because then the developer can fix the software, which means the user's software won't crash. So I use a lot of software, and this is just an example. One of the reverse engineering tools I use, Hopper, crashes occasionally. I like reading crash reports. I grab the crash report, send it to the developer along with the synopsis of what I think went wrong. And he is very happy because he says, OK, yeah, it sucks my product crashed. But because you have given me the crash report, I will find the information about why it crashed and then quickly push out a fix. He's stoked. I'm stoked as a user because the next version is not going to crash as much. Now, sysadmins, many of you all, and security teams, I think, should also be taking a close look at crash reports. And I love this case study from Microsoft. It's now about a decade plus, but I think it really drives home the point of the value of crash reports. So I mentioned that crash reports are generated when programs crash. And in some cases, this will be a result of a failed exploitation attempt. We'll look at some of these, but you can imagine a browser, for example, has a vulnerability that a hacker has uncovered, perhaps as a zero-day. They try to exploit it, but their exploit is not quite right. Or maybe it's not 100% reliable. In this case, what is going to be generated? A crash report. So even back in 2008, Microsoft was collecting and ingesting crash reports and then analyzing them to find indicators of failed exploitation attempts. And they published this interesting case study where they basically bucket crash reports by the number that they see in the wild. And to be fair, most of them are going to be unexploitable bugs, but even those are useful because if they push out an update and everything starts crashing, even if it's not a security problem, that's something they should fix. So they were going through and analyzing that, and when they got to 45,000, they found a crash report that had happened twice across every single Windows computer in the world. So essentially, never, twice. And when they dug into it, what they found, as we can see on the slide, is that it was a failed exploitation attempt where adversaries had uncovered a Windows 0 day, meaning Microsoft did not know of this vulnerability. But by analyzing the crash report, Microsoft, MSRC, could figure out what went wrong and could actually detect or figure out that this was not only a 0 day, but it impacted every single versions of Windows, could be remotely triggered, and would give the remote attacker system-level access, like God mode. This is insane. And so this was really great that, from Microsoft's point of view, the hackers had a mistake in their exploit, which generated a crash report, because then they could understand what went wrong and push out a patch for this, essentially now protecting all Windows users. On iOS, crash reports are super valuable as well, especially because it's difficult to run other security tools on iOS due to Apple's rather strict constraints there. There have been some companies who have really dove into analyzing crash reports on iOS, and as this slide shows, there's some good money to be made there. So I think this shows that on iOS, this is something that is already been dug into and something that startups and other companies are finding very valuable. Crash reports are also a good way to perhaps detect malware. And the reason for this is malware is generally not written as well as security tools, operating system vendor software, applications, et cetera, et cetera. This is first and foremost because maybe malware authors aren't, traditionally software engineers, and or malware is often trying to push the envelope of what it's supposed to do. Might be trying to hide files, access, user passwords in a way that's not really supported. And so, things are going to crash. So the idea is if we analyze crash reports, perhaps we can find something that's on the system that previously remained undetected. One great example is Stuxnet, the world's greatest computer virus ever. How was it discovered? Crash reports. It had a bug in it that would cause computers to crash, which ultimately revealed its presence, which up until then was undetected. Another more recent macOS specific example is a malware known as Zuru. You can see it was originally undetected on VirusTotal. It would occasionally crash, which again meant that if it somehow slipped onto your computer or computer at the company you work for, and then crashed, if you had been analyzing crash reports, very quickly you would have uncovered the fact that something you didn't recognize was faulty, revealing the infection. If you're a malware analyst, crash reports are useful as well. A most recent example is Lockbit. This is a ransomware gang. They traditionally focus on Windows. Earlier this year, they decided, hey, we should build a Mac version of ransomware. Why not, right? Makes sense from their point of view. Well, unfortunately for them, fortunately for us, this initial variant targeting macOS was buggy, which means that in some cases it would crash. So yes, this means we could perhaps detect it by ingesting crash reports, but that was actually problematic to me because I actually wanted the malware to run to completion so I could test my security tools. So one of the tools I've written generically detects ransomware by looking for the rapid creation of encrypted files by untrusted process. This is like a generic heuristic for ransomware. So I actually wanted Lockbit to run. So when it ran in a VM with my security tool installed and crashed, I had to figure out what was going wrong by understanding the crash report. This allowed me then to fix the bug by patching the binary image of the malware for educational purposes only. That then allowed me to execute the malware. It encrypted all the files, or would have, but my security tool intercepted it, suspended it, and detected that. So that was helpful for me to test my tools because I was able to figure out what the bug was in Lockbit from the crash report. I mentioned hackers and intelligence agencies are very interested in crash reports as well. These are actually leaks from the NSA around the Snowden error. Kind of hard to see on the screen, but this is actually a screenshot from an internal NSA presentation that was leaked to the media. And basically what they did, which I think is hilarious, is they took the Windows error reporting pop-up and they changed it to say, this information may be intercepted by a foreign SIGINT system to gather detailed information and better exploit your machine. So back in the day, Windows didn't encrypt their error reports. And so if agency had signal intelligence collection capabilities and could intercept these, they would learn two very interesting things about the system where the crash report was generated. First, crash reports, as we will see, contain a myriad of information about the system that crashed. Language, operating system version, service pack, et cetera, et cetera. And if you are a hacker trying to target a remote system, this fingerprint information is very important because a lot of times you have to customize your exploit based on operating system level, language settings, et cetera, et cetera. So valuable fingerprint information. Secondly, though, they were seeing what was crashing on Windows systems. And maybe these were vulnerabilities in Windows that could be exploited at 0 days. And so very interesting that they were paying attention to that. Finally, though, what I like about crash reports is they are really the source of absolute truth. And we'll dig into CrowdStrike shortly because it's a great case study. But as I'm sure all of you know, a few months ago, Windows systems around the world started melting down, crashing. And there was blue screens of death everywhere. So what happened? Everyone immediately blamed Microsoft and said, what did Microsoft do? What did they do? They push out a bad update, something, something, something. And so everyone, like the media, Twitter, was like, Microsoft sucks. I'm not saying they don't, but in this case, this was not a Microsoft fault. So once we got a crash report, as I will show you, you can figure out exactly what crashed, right? That's like the first line in the crash report. And so very quickly, we could see, look, yes, maybe Microsoft could have designed Windows in a more robust way, but in this case, it was not a Microsoft fault, it was a CrowdStrike fault. Okay, so people are like, now it's CrowdStrike. Started jumping to wild conclusions, making claims about the type of vulnerability, the type of issue, all wrong. People even got the crash report, but because they didn't know how to read it, they would post it on Twitter, draw some lines, and make wild claims like it's a null pointer dereference, this is something that should be detected, blah, blah, blah. It was not a null pointer dereference, as we will see. This got 25,000 retweets, 26,000, so misinformation. If the individual had understood how to read crash reports, and we will go through this, they would have figured out exactly what was wrong and wouldn't have pushed this misinformation. So crash reports, absolute source of truth. Okay, so hopefully now you're convinced that crash reports are very useful for detecting malware, for finding bugs, if you're a hacker, intelligence agency. But now let's kind of take a little bit of a step back and talk about crash report basics. Then we will get into some actual examples impacting macOS, which I think are super cool. Okay, so what is a crash report? Well, as I'm sure many of you know, as I mentioned earlier, it's basically what is generated by the operating system when a program crashes. And the key point here, though, is that it's really designed for pretty much the developer of the software. And as we'll see, it contains things like registers and call stacks and very low-level things. So the average user is not going to know how to read this. And when I started doing security research, I didn't know how to read crash reports. And this is one of the reasons I'm giving the talk, because if we have a basic understanding, we can pull out a lot of very interesting information. So on macOS, where are crash reports stored? There are two locations, basically in under these log folders. They end in .ips. That's a file extension. You can go there via the terminal or via Finder, or the console application will show you. All right, what we're now going to do is walk through a demo. I'm going to show you some source code. We're going to generate a crash report, and then we're going to work backwards from the crash report to show, even if we didn't have the source code, we could figure out exactly what the bug was. Because 99 out of 100 times, you're not going to have the source code for the bug that caused the crash report, unless you're the developer of the tool that crashed. So, buggy code. We can see it's a few lines of C code. What we are doing is we are initializing a pointer to null, and then we are dereferencing it. I'm sure many of you know you can't dereference address 0. You can't dereference null. If you do, it's going to crash. So if we compile this and execute this, no surprises here. It generates a seg fault. If we pop into console, we can see that there is a new crash report that has been generated by macOS, and it's named I will crash because that's the name of the program I compiled. If we open the crash report, we can see some basic information at the top. We have the path to the process. This is the binary that we just ran. This is useful. We have information about the operating system, et cetera, and also the version of the tool that crashed. The versioning information is important for a developer because imagine you've pushed out multiple versions. If old versions are crashing, maybe you've already fixed that, and so this is all important. We also have the operating system version. This is important as well because if it's a bug, perhaps in macOS, it might impact only certain versions of the operating system. Next, we have the crashed thread. Most programs are multi-threaded, so the crash report will tell you what specific thread crashed. In this case, we have a simple command line utility. There's only one thread, so this is the one that is highlighted. It says crash thread 0. Things started index 0 on computers, so it's the first thread, but it's thread index 0 has crashed. And then it also gives us some basic exception information. Here, for example, we can see that it's a sig_v, which is basically accessing invalid memory. And we can see it's actually printed out the address that it's failed, which is 0, because we have a null pointer dereference. So we haven't actually looked at any disassembly yet, but we can already, from this part of the crash report, see that it's likely a null pointer exception. Next up, we have the stack backtrace. This will show you the sequence of calls that were made that got to the actual buggy line of code. And this is very important because a lot of times you might see the line of code that caused the crash, but it might be because something invalid was passed to it. And so having the backtrace really provides some essential context, again, to show you the flow of control that basically caused the crash. So that's very useful as well. Next up, we have the crashed thread state. This is kind of getting into the weeds, but this will hold the registers and their values at the time of the crash. This is going to be specific to the architecture. So on an Intel system, it's going to have the Intel registers. On the ARM, it's going to have the ARM registers. However, this is super important information because, especially on macOS, crash reports don't have a lot of context, but the registers and their states actually do give you a bunch of context. So as we'll see, for example, when a null pointer dereference occurs, that null value will be stored in some register. So we'll be able to see that, OK, that's exactly what happened. So the registers and their context is super, super important. Next up, the crash report also shows you what binaries are loaded. This is helpful because the crash might not be in the main executable, but one of its loaded binaries. It also gives the addresses that the loaded libraries were in memory. And this is useful because of things like ASLR. Binaries get shifted around in memory. And so if you want to open it in a disassembler to figure out what exactly went wrong, you're going to have to rebase it to match where it was loaded in memory, because the crash report is going to have addresses that match to where the binary was on memory. So kind of an important thing to know as well. And then most importantly, we're going to have the address of the faulting instruction. This is the line of assembly instructions, the binary code that was executed that immediately caused the crash. So in this case, remember we had a null pointer dereference. You can see the C source code on the right of the slide. Don't worry about understanding all the ARM disassembly, but the point is the crash report had an address, FF78. If we load up the program that crashed in a disassembler and rebase it, go to that same address, we will get the actual instruction that caused the crash. And in this case, it's a store instruction that's trying to store the value from the W8 register into the address pointed by the X9 register. And if we look at the X9 register from the thread state, we can see it's 0. So immediately we can be like, OK, if you try to store something at memory 0, it's going to crash. So now we know exactly what went wrong. So that's, again, a pretty in-depth deep dive into that. Oftentimes you won't have to go that deep, but I wanted to really kind of get that off my chest. So as we talk about some actual cases where we're going to dig into some rather interesting crash reports, that information that I just covered is relevant. Now, I know this is a conference focused on Apple topics, but I briefly want to talk about a very interesting case study involving CrowdStrike that I alluded to earlier for a few reasons. First and foremost, it illustrates that a lot of the concepts of analyzing crash reports are applicable to other operating systems as well. Now, there will be a few nuances and differences, but if you can understand crash reports on macOS, you will so on Windows as well, which is awesome. Also, CrowdStrike provided just a very timely and relevant case study where we were able to figure out exactly what went wrong by analyzing the crash report, as we will see, before Microsoft said anything, before CrowdStrike said anything, which was, I think, very relevant. OK, so we're going to start with a crash report. This is what a crash report looks on Windows. You open it in WinDBG. And a little hard to see, but what I want to point out is WinDBG will highlight the faulting instruction. Again, this is the instruction that was executed that caused the crash. So that's kind of where we start. Also, there's some context. For example, we can see an invalid memory. So just from the crash report, we can see that what the code was trying to do was read from the R8 register and move that into the R9 register. Where it was moving it is irrelevant. The key thing is it was trying to read it from the R8 register. And if we look at what the R8 register was at the time of the crash, it's invalid unmapped memory. Now, since this happened in CrowdStrike's kernel driver, if you try to access or read from invalid memory in kernel mode, what happens? Boom, right? Box blue screens, crash report is generated, and unfortunately, because CrowdStrike's driver was set to auto restart, it went into like an infinite reboot loop, and the rest is history. So let's dig into this a little bit deeper. So we know that the faulting instruction is, again, number 2 on the slide. It's trying to read from R8. So the question then becomes, why was R8 corrupted? So what we do is we look a few lines back in the disassembly, and we can figure out where the R8 value came from, the foobarred R8 value. And we can see it was basically pulled out of a register. RAX pointed to the beginning of the register. R11 was the index into the register, multiplied by 8 because it was a memory, an array of 64-bit values. And if we look at the actual array in memory, we can see it looks like it contains valid pointers until it gets to index 14 or 20D, which is where the R8 registered. So what we can see is the bug was that CrowdStrike read one value outside of an array, grabbed some random address, and then tried to dereference that address, which caused everything to blow up. So it turns out the bug was actually an invalid out of bounds. Now, I've been talking about how awesome crash reports are. I think this is actually the coolest thing about them. So I tweeted about this, and I got a call from Good Morning America, which is a big TV show in the US. And they were like, hey, you seem to understand like crash reports, and you understand this CrowdStrike thing. Like, do you want to be on TV to explain to the American public what went wrong? And I was like, yeah, sure, why not? I just got home from a party. I was like, I got to shower and sober up, but let's hop on this because, I was in Europe and they wanted to broadcast it at 7 a.m. And so, maybe if nothing else, analyzing crash reports will give you your 15 minutes of fame. And as we can see, like, my mom was like, this is awesome. So, like, hilarious. I don't know if the general American public appreciated my crash report internals. I kept it at a high level, but you did? Awesome. Amazing.
My mom's proud of you, too.
Oh, well, then thank you. I appreciate it. So thanks, CrowdStrike. Thanks, your mom and everyone. So we're going to change gears a little bit now and now focus on some macOS-specific crashes. And I want to point out these are all from my computer. And I wasn't trying to do anything bad. I wasn't fuzzing. I wasn't looking for vulnerabilities. I was just, like, doing my thing. Something would crash, and I was like, ooh, what is this? So let's look at some of these crashes. First, how do we even generate crashes? Well, as I mentioned, you might think you have to do really bad things, but I found one really good way to generate crashes is to write tools, especially security tools. Not security tools doing super funky things, just security tools. And I love this slide because I was writing a DNS monitor, which is a network extension. We know Apple struggles with those. And to be fair, I had a bug in my code. I am responsible for that. So my code crashed. It was my bug. But what happened behind the scenes? First, NSLOOKUP, which I was using to generate DNS requests to test my tool, crashed. And I was like, that's weird. And then Apple's network extension session manager, which is running as root, crashed as well. And I was like, yo, this is not ideal. But actually, I was really excited because now I had 3 different crashes. So one of the takeaways is macOS maybe isn't as robust as Apple would claim. Now, I've picked on Microsoft, I picked on CrowdStrike, I picked on Apple. I'm going to start by picking on myself. So the first crash report we're going to look at impacted one of my tools called Lulu. Lulu is a free open source firewall for Mac OS. I released the version, was doing some testing, and I noticed in certain scenarios it would crash. And I was like, that's not good. So if we look at the crash report, we can see the exception is a SIG bus error, which generally occurs when invalid memory is accessed. But if we look most interestingly at the call back, the stack backtrace, which again is the sequence of calls that led up to the crash, we can see it's deep and repeating, meaning the same function is getting called again and again and again and again. And as soon as I saw that, I was like, ooh, that's recursion. And about a week before, I had very proudly implemented some recursion into Lulu. The idea is when, say, for example, the user installs a browser and has 50 tabs open, if they haven't approved the browser yet, Lulu will detect it and say, hey, browser X is trying to access the internet. Now, the browser is going to do that like 50 times in a row. Lulu shouldn't show 50 prompts. So it shows one prompt, queues up the rest. When the user either approves or denies it, it applies that same logic to all the other connections that have originated from the browser, even if they're asynchronously. And I said, the way I'm going to do that is recursion. I remember learning about this in computer science class. I have never used recursion. Here's a perfect opportunity. And it was genius, and it worked well, save for the fact that on macOS, the stack is actually pretty shallow, which means every time you make a recursive call, it pushes information about the call onto the stack. So if you go too deep in your recursion, you will just run off the stack. Now, this is different than like a stack overflow. This is actually stack exhaustion. So it's not exploitable, but it will cause a crash. And it turns out if you have about 300 or so instances of your recursion, you're going to run off the stack. And so that was exactly what was happening. The fix was simply to implement this iteratively, which is a little soul-crushing because it meant that I, even to this day, have never used recursion successfully. One day. Next up, we have Yara. Yara is a very popular third-party pattern matching library. It's used in a lot of security products for AV signatures. I was implementing it in a tool, and I noticed that when I went to scan certain binaries, it would crash. But if we look at the crash, it was a code signature invalid crash. And this was interesting because my tool was validly signed, notarized. There was nothing wrong with my code signature, but macOS was somehow getting confused. So what I did was I reverse engineered Apple's private implementation of Yara and compared it with the open source one. And I noticed that when Apple mapped a file into memory to scan, because you're, for example, using Yara to scan a file to see if it's malware, you're going to map it into memory, scan to see if any of the signatures match, et cetera, et cetera, et cetera. The way Apple was doing it was with a flag that was map private and then, most importantly, map underscore resilient code sign. And if we look at the open source Yara implementation, they were not using that flag. And this was problematic because what this meant on macOS is if you don't map data with that flag, even if you're just mapping it as read-only to scan, if what you have mapped has an invalid code signature, when macOS or when your code goes to read it, it says, oh, wait, this has invalid code signature and crashes, which is kind of insane because, again, we're just mapping it as read-only. We're not executing these bytes. But this would mean Yara would crash when trying to scan a binary that had an invalid certificate. So the fix was simply to add that same flag, which basically tells macOS, like, yo, chill. I know what I'm doing. I'm just loading this into memory. I'm not running it. I'm just scanning it. It's not executable. Like, I don't care if the code signature of what I'm trying to scan is invalid, because also I have no control over it. And so I submitted that to Yara, and they were awesome. They fixed it right away. But they were able to do it very quickly and did give me some kudos, which I'm very proud of, because I submitted the crash report as well, and I said, hey, I dug through the crash report, and this is exactly what is going wrong, and this is how you have to fix it. Because it was one of these things that was like happening very rarely, and if I was just like, Yara is crashing on macOS, they would be like, that's really not helpful. So again, as a user, really, really beneficial if at least you provide a crash report, and if you understand it a little bit to be like, hey, I was scanning an unsigned binary, and it looks like this, and this is what Apple's doing. The developer will more than likely be super stoked and fix the software very quickly. Next up, we have a crash in Adobe's Crash Reporter. This is a silly bug, but it's kind of meta because I love like the Crash Reporter is crashing, right? It's like, everyone's code sucks. And if we look at the crash report, in this case, macOS tells us exactly what is wrong. It's saying, hey, they're calling release with null. So you can't like free null memory, right? Like that's almost as bad as trying to access null memory. And so if we look at the stack backtrace, we can see the sequence of calls that led up to the release. And this is actually an important thing to note because the crash itself is happening in Apple's CF release function, its system API. That API is not buggy, but if you pass it a null, it's going to crash. I mean, maybe it could check that it's not null before trying to release it, that API. But generally, system APIs are like, look, if you pass us invalid data, like, we're going to crash. And that's fine. That's a decent design. So in this case, we actually have to figure out why null was being passed, and this is why looking at the stack backtrace is super important. So if we do that, we basically can see, this is closed source, so we have to disassemble it. They are getting an object by calling this SC dynamic store create API. And then if you follow the arrow, you can see that they're always freeing it. The problem is, in some cases, this API can return 0, null. And in that case, you shouldn't try to free it. So Adobe should check, as we all should, that if getting back a pointer to something, it's valid before you try to fix it. And the fix is, as ChatGPT explained to me, is basically just checking it's not null. So maybe Adobe should use ChatGPT too. We all should. OK, so I talked about that a lot of times a crash will be in an Apple API, but that API doesn't actually have a bug. It's that you're calling it incorrectly. But in some cases, Apple's APIs are buggy. So here's an example of that. So one of my other tools, Do Not Disturb, will alert you when your laptop is opened by an unauthorized user. Funny story. This is actually 100% true. I was in Moscow at a conference, and I was like, I should go on Tinder when in Moscow. So I matched with this beautiful Russian woman. Again, this is 100% true. And she was like, I want you to take me to dinner on this date at this time. And I was like, wow, yeah, sure, cool. So we meet up. 5 minutes in, she pulls out a business card. She's like, I work with the Russian government. I was like, wow, y'all are using Tinder to like troll and like connect with foreigners? Genius. But at the same time, I was like, OK, she's either trying to like build trust and rapport, which that's a great way to like coerce people, and or while I'm out to dinner, there's like an evil maid attack going on, which is like someone breaks into your hotel room, and with physical access to your MacBook or your iPhone, it's a lot easier, especially 10 years ago, to then gain access to the content on that. I was traveling with a burner device, but even still, interesting. Anyways, that was the inspiration about Do Not Disturb, which was like, hey, if someone did break into my hotel room, opened up my MacBook, I want an alert on my phone being like, yo, someone's poking around. OK, so I ran the tool, and it would crash when copying a public key. And it would crash in an Apple security API. And I was like, I looked at my code many times, and I was like, I think I'm doing this right. Like, I'm just, I'm passing it a valid key. Like, this shouldn't be failing. So I decided to dig more into Apple's API, both to figure out maybe there's some weird corner case that I wasn't fully initializing or aware of, or maybe there was a bug in Apple's code, which in this case there was. So it turned out, long story short, that I, from the crash report, could find the faulting disassembly. And since this part of macOS was open source, I could then map that to Apple source code, which is always great. Like, the disassembly is awesome, but if there's source code, like, that's way easier to read. So what we can see is they're checking an error value, and if it's not null, they are dereferencing it. And that's the line of code that was causing the crash. So I said, that's weird. And so I looked a little closer, and turns out what they were doing is they were declaring this error pointer, but never actually initializing it. And then on certain cases, they would dereference that. And we can actually confirm that, because if we load this code into Xcode, we can see that the compiler actually throws a warning and says, yo, you're accessing a pointer that you've never initialized, which is a big no-no, because that means whatever on the stack now becomes what the pointer tries to be. And there are scenarios where, as an attacker, you can influence that and maybe take control. So that was good. Apple actually assigned a CVE, fixed this. This was in one of their security APIs. And so again, the only reason I was able to figure that out was from the crash report. Next, let's move into the kernel, because when the kernel crashes, we know the whole box goes down. Most people get really annoyed. I get very excited, because I'm like, ooh, maybe we have a kernel bug. So if we look at the crash report from the kernel, we basically get the address of the faulting instruction and the address of what appears to be some unmapped memory. So what we can do is we can take that faulting instruction, kind of seeing a pattern here, right? Go and figure out what line of assembly code triggered that, and then figure out what was going on. And again, this part of the kernel was open source, so I was able to find the line of code that was causing the panic. And basically, it was the highlighted line where they were trying to check to make sure a sequence of bytes were null terminated. In this case, the name of a socket. And for some reason, that was crashing. Well, it turns out they had an off by one error, very similar to CrowdStrike. Apparently, it's a common bug, where what they were trying to do is actually look one byte outside the array to see if that was null terminated. And this normally was fine, except for the very rare scenario where the sequence of bytes ended on a mapped page, and then the next page was unmapped. So we can see on the slide that would be problematic, because then if the code tried to access the next byte, as we mentioned earlier, accessing unmapped memory in the kernel will cause a panic. So this was an off by one, and you might be wondering, like, is this a cool bug? Not really, because it's not something that's exploitable, and it's just like an invalid read, not something you can normally do. I mean, the box would panic, but as an attacker, we can't escalate our privileges or anything else. OK, so I reported this to Apple. And what was Apple's fix? Apple's fix was, and this is their comment as well, it says, make sure the path is null terminated, and they use a strl copy function. Strl copy is a safe str copy. It'll copy memory from one location to the other. But what does it need? It needs a null terminated string. And so if the string is not null terminated, it will just keep copying bytes and bytes and bytes and bytes. So what Apple actually introduced is a kernel information leak, which means now we can read arbitrary kernel memory, which is insane, because we can get pointer values for other exploits or very sensitive information that resides in kernel memory. So again, this was like super frustrating. I was like, Apple, I found you a bug. And they're like, we fixed it. I'm like, you made it worse. And I was just like, oh my goodness, what is going on here? And so while they were fixing that for the second or third time, I said, you know what, I'm going to look at this function, because clearly nobody knows what's going on, and where there's smoke, there's fire. And I looked a few lines up, and there was an unbounded B copy, which led to an exploitable heap kernel overflow. And this was a few versions of macOS in the past. But again, from a crash report, we got Apple to introduce a worse bug, and then found other bugs as well. So interesting. OK, this last one is not on my computer, but was in a friend's iOS device that I would inadvertently trigger. So my friend, again, it's a true story, from Taiwan. I love emojis, as we can see in my slides. And so I would text her like things about Taiwan, and I would always like add the Taiwanese flag. And she's like, Patrick, whenever you text me, my phone crashes. She's like, are you hacking me? And I was like, rude, for two reasons. One, I don't hack my friends, and two, my hacks don't crash, right? So I was like, no, something else is going on here. She's like, maybe the Chinese are hacking me. And I'm like, I'm sure the Chinese are not hacking you. But either way, something is going on. Let's figure out what. So it's really hard to like debug iOS. And this is also like her personal device. So like the only place to start is the crash reports. So we grab the crash reports, and we look at the stack backtrace in the crash report, and we can see that the sequence of function calls right before the crash are in the core emoji library, which kind of makes sense because it happened when I would either send her a Taiwanese flag, or she would type the word, as we can see on the screen, Taiwan, which would have iOS pop up like the suggested emojis, which would also include the Taiwanese flag. So from the crash report, we find the faulting instruction, and basically, long story short, they're calling a string comparison routine with a null pointer. If you try to compare a string against null, we're seeing a pattern here, crashes, right? Nulls are bad. But why? So we look a little back further, and we can see what iOS was doing. It was getting the locale, I don't know how to say that. Basically, the language settings of the iOS device. And then it was comparing it against CN. What's CN? China, exactly. What Apple was trying to do was basically say, if this is a version of iOS that's running in China, because the Chinese government doesn't like the Taiwanese flag, we are going to appease them, and we are going to not display it. Unfortunately, Apple's code to do that was buggy and would crash certain devices. But while it's just a null pointer exception that was kind of uninteresting, it revealed the fact that Apple was acquiescing to the demands of the Chinese government and censoring devices in China, which is a whole separate discussion. But for a company that prides themselves on doing what's best for the end user, that's not cool with me. And again, we were able to prove this via crash reports. Hooray. OK, I want to end by talking about some recent crash reports that impacted the latest version of macOS up to macOS 15. So these were, at the time, all 0 days. And again, I was not actively hunting for 0-day vulnerabilities, just going about my day on my Mac, found some interesting crashes that did reveal some very interesting security bugs. So the first one is in Apple's Keychain Access app. As you all know, all the goodies are in the keychain. I guess now the password app has kind of taken over, but prior to macOS 15, your passwords, private certificates, authentication tokens, all the goodies. So obviously, if there is a security issue in an application that has access to the keychain, that's problematic. Keychain Access app, if we dump its entitlements, we can see it's able to access the keychain, obviously. So again, issues in here are more problematic than an issue, say, in Calculator or TextEdit. So the crash report is interesting because it shows a pointer authentication failure. If you see a crash report with a PAC violation or a pointer authentication failure, this basically means memory has been corrupted. The operating system has detected it, but the fact that there's memory corruption opens up a lot of doors for attackers. So if we look at the stack backtrace, we can see that the crash originated in the sec certificate get data function. So let's take a closer look there. Since this was happening on my box, I could just attach a debugger to the Keychain Access app, perform the same sequence of events to trigger the crash. And since I had set a breakpoint on the problematic API call, I could see how it was being invoked, which, as we'll see here, actually shed light into the underlying issue. So in LLDB, if you type PO, that's how you print out an object. X0 is the X0 register, which on ARM systems contains the first argument that's passed to a function. And here we can see if we print it out, it is a sec CDSA keyref. I don't know exactly what it is, but it's a keyref. Remember that. If we go to read the documentation for this API, it says that the first parameter should be a certificate, not a key. So this API takes a certificate, not a key. And those are two wildly different objects in memory, totally unrelated. So if you pass the wrong type of object to this API, you basically trigger what is known as an object type confusion vulnerability, which opens up a lot of possibilities for an attacker. Next up, we have an interesting crash in Apple's system extension daemon. So about 5 years ago, when Apple kicked everyone out of the kernel to avoid a CrowdStrike-type fiasco, what they had to do was implement new logic in user mode that would facilitate third-party security tools that previously lived in the kernel. So for example, a tool like Lulu, Used to be a kernel extension. That's how Apple said do network packet filtering back in the day. Now you do it as a system extension or a network extension. And to facilitate that, Apple has created new daemons like the system extension daemon to manage that. So I was attempting to load one of my tools, and my tool wasn't configured correctly. That's on me. But surprisingly, when I tried to load that tool, it would crash the system extension daemon, which was strange because that's like running with root privileges, and like you shouldn't be able to like cause it to crash. And so that was interesting. If we look at the crash report, we can see that rather helpfully it prints out that it was because of an assertion failure. And if we look at the disassembly, we can see that on certain error cases, the daemon decides just to crash instead of like handling it gracefully. I was triggering it in rather inconsistent assertion, but I decided to say, hey, can I look through the rest of the code to find other scenarios where the system extension daemon is throwing exception, is catching an exception and then deciding to crash. And it turns out there are many of these. One of them is if you try to load a system extension that has the number of architectures set to 0, the system extension daemon will detect that, as we can see in the disassembly, print out an error message being like, yo, you're trying to load a system extension that has an architecture count of 0. And instead of then just like ignoring it, it decides to crash, which is an interesting design decision because this means that unprivileged malware, for example, that has somehow slipped onto the box, can actually continually trigger this crash, which means other security tools can't load. Because if the daemon is continually crashing, it can't service other attempts. So this isn't like a super exploitable bug, but does have an impact and revealed, I think, a very questionable design decision in Apple's system extension daemon, which is, hey, anytime I encounter a state that I don't really like, I'm just going to crash, instead of being like, I'm going to ignore this. Strange. And then the last one I want to talk about is in Apple's network extension session manager, because this one actually has some problematic impacts as well. And it's kind of actually an interesting bug. So again, some of my tools are network extensions. I was trying to load them. Again, I had a slight misconfiguration. I don't read the documents as much as I can. But the upside to that is when I do something wrong, a lot of times it triggers issues in Apple's code, which leads to really interesting bugs. So in this case, we have the crash report, and we can see that it crashed in the obj respond to select method. And in the call stack, we can see that they were initializing a string with a format. Two things. If you find a crash in the respond to selector method, this is called all the time to introspect an Objective-C object. If the object it's trying to introspect is invalid or corrupted, it will crash there. So again, not a bug in that API per se, but that indicates some type of memory corruption, object type confusion is going on. So we need to figure out why this method was called incorrectly or passed an invalid object. So if we look back in the disassembly, we basically find that when a certain error occurs, what the code is trying to do is print out a localized error message. And the code at the top of the slide shows how they try to get the localized format string. And we can see they pass a key, invalid mock service name, and then they pass the format string, which is %@, %@, %@, %s. Now, format strings are like populated at runtime with actual values, but you have to tell the computer, or the code rather, what type of value it's going to expect. So a %@ means an Objective-C object, whereas a %s means a C string. Very important to get these right. So they make this call, and they get the format string that you can see. This is the error message they're going to print out, and they're going to populate it with values from the extension that's invalid. And if you notice, the last format placeholder is not a %s, it's a %at. That's kind of problematic. And we can also see in the code that it is actually a C string, not a string object. So again, since this is on my box, we can debug this, and we can see that this is exactly what's going on. They are basically passing the wrong type of an object to a format string initialization method. So again, it's expecting a %s, and they're presenting, or they told the code, hey, this is going to be an Objective-C object, and then they pass in a C string, which is just a sequence of bytes. That's really bad, and that's going to cause a crash. Now, what is the impact of this? Well, the problem is when the network extension session manager goes down, it takes down with it every network extension product as well. So if your system has a firewall that uses a network extension, which they all do, this means unprivileged malware can make a request to the network extension manager that's like, load me, and the network extension manager will process that invalidly, crash, and then unload all the other security tools. So one of Apple's big claims when they kicked everyone out of the kernel was like, hey, we're still going to make sure that malware can't unload the security tools, because that's probably the first thing malware would try. But with this vulnerability, we're kind of back to square one, where malware could first trigger this crash. All the network tools are now gone, and then it can do whatever it wants without fearing detection. And we can see that in this case, this impacts Lulu. Not Lulu's fault, but it gets an unload message from the operating system and gets forced to unload when the thing crashes. OK, now I could talk about these all day. I'm going to grab some water, getting a little hoarse. This slide, though, I wanted to show that there's lots more crash reports. So maybe next year we'll have a whole nother discussion about these. And you can see they're an interesting stuff, like Apple's payment message stuff, virtualization frameworks. Yeah, lots of exciting things. OK, I want to wrap up by briefly talking about how to collect and analyze crash reports, because hopefully I've shown you they're very, very interesting. All right, few straightforward steps. Really straightforward to programmatically watch the crash report directories, and then when new files show up here, you can grab them and ingest them for human or automated analysis. The easiest way to do this is with the endpoint security framework. I know many of you are familiar with this. Basically, you can create a file monitor or a file watch. Don't worry about the specifics of the code. This is maybe just for reference. But basically, we can create a program that watches the crash directories, and anytime a new crash report then lands, we can grab them. So now what do we do? Well, automatically analyzing crash reports could be a whole talk unto itself. I will point out that most crash reports are junk. They are UI bugs that there's an issue in some rendering library, can't be triggered without user interaction, blah, 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 blah. So some things are, first and foremost, is it a process of interest? So if calculator crashes, I don't care. Most people shouldn't care. But if it's a system daemon running as root, OK, might want to dig into that. Is it a browser that's processing remote data? OK, maybe. So first thing is it a process of interest? Then if it's a crash due to an assertion, I generally ignore those, because that means it's handled and it's just going down, unless, as we showed in the case of the system extension manager, that it's an assertion we can trigger that then, for example, takes down other security tools. And then third, if it's a crash on the main UI thread, it's often just a rendering issue. Apple's rendering libraries are kind of buggy. And again, from an exploiting or from an attacker's point of view, that's not really interesting, because that requires user interaction. It's we've probably all been scrolling around in the browser or Xcode or something, and it crashes. That's not really that interesting. But if it's a background thread, maybe it's processing an image from an email attachment that could be malicious. So kind of dig into theirs. All right, conclusions and takeaways. OK, crash reports, awesome, right? You can find bugs, which you can fix or write exploits if that's your thing. No judging. You can also uncover malware. You can uncover flaws in the operating system to help Apple make it more secure. And in some cases, you can find failed exploitation attempts. So again, raise of hands now. Who here loves crash reports? OK, awesome. We're stoked. More than we started with. So that's a win. Awesome. And I had to put a banana in the slides. I have no idea why. So after the talk, maybe someone could explain. But I don't know. But there was one with Mario and crashing. I was this is perfect. This was made for my talk. Okay, if you're interested in learning more about malware and these techniques, I've written a few books on the topics. And the great thing is these books are free online. So you can pop over to taomm.org. Each chapter is fully available there. Version 1 or Volume 1 has been out for a while, and Volume 2 will be published, I believe, in January or February of next year. And so if you're interested in macOS internals, malware, debugging, kind of a lot of the topics I touched on, definitely check those out. Briefly want to thank the companies and products that support the Objective-C Foundation. Many of the companies are here today, so personally, just thank you. They are the ones that help fund my research, help make the books free online, help us organize the Objective by the C conference, all the free open source security tools. So just want to take an opportunity to thank them. Also, again, want to thank Patrick and Kiki for organizing this awesome conference that I will come to, even though it's cold here, but today was awesome. I brought the sun. You're welcome. And then also thank you to all for attending this pretty nerdy topic. I hope you all got something, a takeaway. So I think we have a few minutes for questions. I'm deferring to Patrick on that. If there are any questions, I would be more than happy to talk. I will also be at the event tonight, so if you want to talk about crash reports, I love talking about it.
Well, you can maybe get him outside, and he will be at the bash tonight as well, so you can pump him for questions there.
Come
as
bash,
well.
yeah.
Bash.
Awesome. Well, again,
Great.
thank you so much. Thank you,
Thank you.
Patrick, and thanks you all.